Good morning, everyone, and welcome to the 14th ETP4HPC webinar. We will have three speakers today, Valeria Bach from Fraunhofer, Chaima Boaza from Pascal, and Daniele Ottavini from Cineca. They will present you an ETP4HPC white paper on Quantum for HPC. I am Maria from ETP4HPC office. I will be your host, and two of my colleagues will help us today. Pascal will take care of the chat and Michael will moderate the session. Before we start, a couple of useful information for you. So this webinar is recorded. You will receive the link to the recording on Monday. The webinar is in listen-only mode, so you can communicate with us, ask questions via the question panel of the GoToWebinar control panel. You can ask questions or send your remarks there anytime during the webinar. We will share the questions to the speakers in the chat, so you can see them, and we will answer these questions during the Q&A session at the end of the webinar. From the control panel, you can also download the handouts. I uploaded there the slides of the webinar and also 4 of ETP4HPC white papers. One of these is the quantum one. So looking at the agenda, after this introduction, Valeria, Chaima, and Daniele, they will give one common presentation, and we will have approximately 20 minutes for the Q&A session before we close the webinar at 12 today. So let's start. Michael, could you please take it over and present our topics? Thanks.
Sure. Thank you, Maria. So welcome everybody to this webinar. You see on this page that we have decided last year to generate also white papers, not only SRA documents, big documents, and you see that we have already 4 white papers coming from ETP members on the so-called Zenodo platform. You get there by clicking on the ETP4HPC website, and then you see up there on the right Zenodo. You go there and you see these 4 white papers below here, and also 2 TCI white papers. And there are more to come. We're expecting still another 5 to 6 over the next few months, so stay tuned. And I would like to welcome very much Valeria, Daniele, and Chaima today. You need to think about this. The team was not existing 8 months ago, so it came together. And they were all very busy because they had to work so much on getting project proposals done. And then within extreme short time, they produced this white paper. And this is excellent. So congratulations to you as a team. Everybody should know that the content, most of this content also goes into the SRA 5, which is planned for mid of next year, of course, with some updates. And last but not least, when you look to the plans of Euro HPC for next year, work programs, ideas that they're tossing around, there is a strong trend for investing heavily into quantum-based technology for high-performance computing. So you will see certainly work programs coming out, and we hope that we can influence these work programs also through the contributions from the ETP white papers like this one, maybe more work in the SRA 5. So with this, Valeria, Chaima, and Daniele, the floor is yours.
Okay, I think you have to give us the presenter rights.
Well, maybe what we should do.
Just a second, I will do it. Oops. A second.
Okay, I can see something, and yes, I've got it, I think. Okay, let me push some things around a bit. Okay, fine. So I'm going to start the presentation on of this webinar on Quantum for HPC, and then at the end, my colleagues Chaima and Daniele are going to take over. I would like to mention that this is not the whole group who has written the white paper on which the webinar is based, but we had quite a lot of authors here who were intensely contributing, and I have put all the names down so that you can see them at least now in the beginning. So what's the motivation? Why are we doing this stuff? That's because quantum computing has the huge potential to provide an exponential speed up in compute. And this can actually go to very different industries such as travel and logistics, chemistry, pharmacology, climate modeling, financial analysis, cryptography, and there might be even more which we don't think about at the moment. So we are seeing here a huge potential. That's probably also why a lot of people are listening to this webinar. But one has to be also careful. The timing for the commercial relevance is still unclear, and that's also to take into account when you're getting too excited about quantum computing, then you should think about that too. We will not replace, or quantum computing will not replace classical computing in the foreseeable future. So even if we are seeing a quantum advantage, the system would need to scale to much larger extent to actually replace everything. And then it's not clear if this is actually something you want to do. What you want to do currently is to develop a quantum ecosystem, and that's where we are looking at from an HPC perspective. Oh, sorry. Keep in mind, this is not a quantum computing seminar, but a quantum for HPC seminar. So we are looking a lot into the HPC perspective. And here we are looking at system level. So how do quantum computing technologies, how can they be integrated into HPC clusters? We're looking at programming level. So you have disruptive ways of programming the devices, and you need to develop a full hardware-software stack. We will go into that a bit later too. And then it's also interesting to look at application level. So to look at which applications does quantum computing actually lead to a disruptive change, and which can it solve, which are currently compute intensive or even intractable problems, and which could become tractable in future. And that's also important because of the audience we would like to present to, because the audience is an HPC audience, clearly. So HPC algorithm developers who are interested in which applications can actually really benefit from quantum computing, scientists interested in the co-design of quantum hardware, benchmarking, possibly also members of the HPC centers who would like to get an update to see what will be coming up in future. I would like to go on with the key insights of the white paper. And the key insights are really, we are seeing the emergence of quantum-enabled solutions, but again, no industrial relevant application with quantum advantage yet. However, as many of you already know, there have been groups reporting a quantum advantage, very often with applications which were quite synthetic for the purpose to show that there's a quantum advantage, but also there are first applications upcoming for scientifically interesting programs, such as a paper from Pascal this summer. The race to hardware, however, is still open. There are a lot of quantum computing technologies on the plate currently, and we think that at least in the short and medium term, we will see multiple quantum computing technologies which are successful. And turning to application areas, there are 3 application areas that are especially important: optimization, quantum chemistry, and quantum machine learning. And what is important is that application-centric benchmarks are needed, because we are seeing multiple quantum computing technologies. We are seeing several application areas which are important, and the benchmarks need to be there in order to compare, in order to know where we are at the moment. Also, most of the applications we are seeing at the moment are hybrid, so an effective integration of quantum and classical computers is necessary, and options for this integration need to be analyzed. Because the systems are growing, currently we are seeing quite noisy systems, we are seeing quite small systems, but still they are growing at the moment. And therefore there are new challenges upcoming for the hardware-software stack, for the deployment, but also for the emulation of quantum computers. So this is where our key recommendations are derived from these insights. And this is, do not lock into one technology too soon, because we do not know who will win, or if there's one winner or several winners at the moment. And therefore, what would be important is that you have an application-oriented benchmark suite, which would also help you to compare the different technologies and compare them with something that's really interesting for everybody. And to promote the establishment of a HPC quantum computing ecosystem with open standards and a common entry point to quantum computing implementations. Because what you're seeing at the moment is that very often the vendors are providing a lot of this ecosystem, and that's sometimes not good, because you're missing the standards. Of course, this is not the fault of the vendors. They need to make their systems usable, and that's clear for everybody. But it's something that I think we should think about in the next years. Then, because this is a fast-moving field, we are seeing these short technological cycles. So the point would possibly be that one has to be careful at where to deploy the first quantum computers in Europe initially. And it might be a good idea to do this at public institutions because of the update cycles. But if you do that, then you have to involve the industrial partners at an early stage to keep them in the loop. Then the key recommendation for us, of course, one of the major one for the HPC view is the integration of HPC and quantum computing, and that has to be done in a very efficient manner in order to also have an optimized overall runtime. And what is often forgotten is that a workforce needs to be built which is familiar with quantum computing. So I'm moving on to the quantum computing hardware technologies. However, this is not an overview over the technologies. This is again looking from the HPC point of view. So I have put down like this plot with some technologies. It's not an exhaustive list. It is a very, very old paper, but some of the stuff is still being researched and has been partly also successfully deployed. So it looked like a good plot to start with. However, there are multiple technologies in use. There are technologies which can give you a universal quantum computer, and there are also things which are much more specialized. And in the rest of the presentation, very often we are referring to the universal quantum computers, but that's another thing you have to keep in mind. And yeah, things are quite complex here, really. Also, the technology readiness levels of the different technologies vary widely. So at the moment, we are seeing that superconducting loops, trapped ions, Rydberg atoms, cold atoms are progressing really nicely on these technology readiness levels. However, it doesn't mean that other technologies might not be as good and can be used in future. What is difficult from our point of view is to make a prediction about the scalability, because the systems are very different. They are relying on different parameters, and it's not clear. Like, even if you have a feeling, okay, this technology can scale very well, very often there are engineering challenges which are difficult to foresee. Currently, all systems are relatively small, so we are seeing that they are breaking the 100 qubit threshold right now, but not much more than that. And most of them are not fault tolerant yet. So here again, we are seeing in small systems that quantum computing gets fault tolerant, but then you can't do the error correction because you don't have enough qubits anyway. What needs to be resolved, and what is probably the most important part here on this slide, is the qubit needs to be resolved, the characteristics of the qubit. So you need to have a fast setup, long coherence time, less or no sensitivity to the environment, to noise in that case. You would like to have a better error correction, which goes along possibly also with the characteristic of the qubits, but also means that you need to scale. You need to scale to quite large number of qubits with good characteristics. And and that of course is the next point, the scalability and also the ease of use. So currently a lot of the systems need to be cooled, and it's a question if, for example, for the cooling, if there would be other solutions in future, and one can think of other scenarios for the ease of use. The next slide is on applications and algorithms. So currently we are in the noisy intermediate scale quantum computing era. So currently it is recommended that you only exchange the computational intensive parts of the HPC applications with quantum algorithms, because your quantum circuits have to be quite shallow and quite small in order to work. Otherwise, you will not get a result because of noise or decoherence times. So, so the algorithms which are currently on vogue are hybrid quantum algorithms. So this is a difference compared to the very first wave of quantum computing algorithms, which are well known, which is, for example, Gruber or Shor, and which are giving you kind of predictions about complexity theory, and you can prove that quantum computing will give you a speed up. These hybrid quantum algorithms typically rely on the variational principle. So you are kind of trying to go down to a minimum, as it is depicted in the plot. These algorithms are successful at the moment due to their needs on the quantum computer, which can be done at the moment. However, you cannot really prove that they will be faster than their classical counterparts. So the main domains that we are looking at the moment is quantum chemistry, optimization, and quantum machine learning. So as it is depicted in the figure, for example, in quantum chemistry, you want to find the ground state, and you're doing this part of evaluating the Hamiltonian in the quantum computer, and then trying to optimize again the parameters for the next round of computation, and then try to go into a minimum state here. The next page is on benchmarking. So benchmarking assesses the quantum computing technologies, and I've shown here a pyramid of of the benchmarking. So you can do it on different levels. You can do it on device level. There you would check the fabrication and device design. On subsystem level, where you would check the calibration, and on a holistic level, where you check much more like compilation, or if you do it for an application, you would also check how fast the application runs. So because of this different level, you always assess something different, like the properties of the technologies on device level, which is helpful to move to pilot lines for bigger productions, and also would be helpful for standardization activities for hardware technologies. When you go to this holistic level, and you even go to application-centric benchmarking, what you can gain here is that you can compare different platforms. And for example, it might be the case because they have quite different characteristics that you find an adequate system for a certain application. And that would be very helpful to get to this point. We are not there yet, but it would be very helpful. There is currently no generally or widely adopted benchmarking suite available for application-centric benchmarking, but one can say that Atos has done a first step in this direction with Q-Score. What one has to keep in mind with the application-centric benchmarking is that you are not only testing your application and your algorithm, but also the software stack, which is below that, and the technology. So you're testing a lot of stuff together, and each of them has to be optimized in order for this to make sense. So I would be handing over now to Chaima, who will talk about the software hardware stack.
Thank you, Valeria. So good morning, everyone, and thank you for being here. My name is Chaima Bouaz. I'm in charge of business development at Pascal. In this section, I'll be presenting the software hardware stack and the integration system, so how we can integrate quantum devices within HPC facilities. So let's start with the software hardware stack. Today, the technology is still in an emerging phase, as Valeria explained, and even if most attention is drawn today to the development of the hardware, we still need to build efficient software stack in order to have an optimal performance of the full system. And today, we identify three main topics that need to be discussed more in details and taken into account for the next phases. The first point considers the software stack that is used to control the quantum device. And today, the software stack that exists still mostly provided by the hardware vendors and tightly dependent of the technology underlying. And an important effort from all European actors is needed to improve this software stack as well as the hardware. And this is, for example, the reason why there is a dedicated call in Horizon Europe, which is focused on the development of software stack. We strongly believe that standardization can be a key in order to allow a fixed interface design between the different software components. So today, it makes sense that each hardware vendor is developing its software stack, but with time and the development of the technology, we will be facing more challenges, especially when we go for larger quantum systems. For example, how to map efficiently a quantum algorithm on the device. This will be an optimization problem in itself. So we need to figure out how to do it efficiently. The second point, it's about the programming tools. Again, today, the programming tools that exist still much dependent on the underlying technology and in general developed by the hardware vendor, even if we have some exceptions. Well, at this early stage, it remains more efficient actually to have a low level of abstraction and to consider the strengths and weaknesses of the device when developing the algorithm or using the tools to program it. However, on the mid to long term, programming tools should be developed towards more hardware agnostic direction and higher abstraction levels. The third point is about scheduler and runtime, and this is very important from an HPC perspective. So the scheduler or runtime system will be orchestrating all the tasks that need to be run either on the quantum system or the classical system. As Valeria explained, most algorithms that are developed currently and used are variational algorithms, so hybrid applications that use both quantum and classical capabilities. And having an efficient distribution of the task is very important, especially when we use these hybrid programs. The total runtime will depend on the latency between the classical and quantum systems. So we need to figure out which is the best way to make them interact and talk to each other. So to conclude on this slide, the key takeaway is the fact that software and hardware stack are tightly linked together and need to be improved together to provide an optimal performance. Next slide, please. So here I'll be talking about the integration of quantum system within HPC. We talk about
I have lost
GPUs, so quantum processing units, in an analogy to CPU and GPU. Sorry?
Chima, we are losing you sometimes.
So it's is it working now?
No, no. I think
me?
you have a bit of a bad connection. Shall I take over, or do you want to try once more?
Or switch off the camera.
Is it yes. Yeah, I'll try this.
Yes, Shaima, please. Yeah.
Can you hear me? Okay, great. So I take over from this slide. So in the integration model, as I said, I don't know if you heard it, but we talk about QPUs, quantum processing units, in an analogy to GPU and CPU. And we see these quantum processors as accelerators that will be integrated within existing infrastructure to help on some specific tasks that are difficult to solve with classical computers or even out of reach to classical computers. And when we look to the different integration models, we identify two big categories: the loose integration model and the tight integration model. I'll start with the loose integration model. So the loose integration model, it means that we have the classical system and the quantum system not directly connected together, but communicating through a network or communication channel. And here again, we identify two different models, the standalone and the co-located. The standalone model means that we have the quantum device and the classical device located in two separate positions, physically in two different locations. The co-located means that we have the quantum device and the classical device within the same facility. Each model has pros and cons. So for the co-located model, the pros are the easier data security implementation. Since we have it within the same facility, we don't have external communication channels. So it's easier to protect the data, especially when we are working with sensitive data. And secondly, the synergies from having both HPC and QC system at the same site. So the communication between the different ecosystem, the different communities can be very relevant and useful for the optimal performance of the system. The standalone model will benefit from the optimal accommodation of each system. So HPC and quantum computers will require different accommodation environments. For example, for quantum devices, we need a very controlled environment in terms of temperature, vibration, etc. And we will have higher modularity in this standalone model. The other integration model we looked at, which is the tight integration model, this is more for the long term. So we mean by this having QPUs on chip that can be directly connected and integrated within HPC systems, so on rack with CPUs and GPUs. This will probably provide low latency, but it requires multiple and significant advances in the technology. All directions still need to be investigated more and tested to see which model it's a best fit and in which direction we need to continue. And now I hand it to Daniele.
Okay. Yes, thank you, Shaima. I will take it from here. I'm Daniele Ottaviani from Cineca. I'm the coordinator of the Quantum Computing Lab, and thank you for being here. It's an honor for me. And today I will speak about emulator for quantum computing in HPC devices. So first of all, what is a quantum computer emulator? With an emulator, with quantum computer emulator, we intend a software that can emulate the behavior of a quantum computer. Okay. So to think about it, the simplest idea is to create a software that implement the same mathematical procedure that you do on paper to write a quantum circuit. Okay. So if you implement this computation into a classical computer, you obtain a simple and very efficient emulator for a quantum computer. And we know that a quantum circuit is a sequence of a certain number of quantum gates on a certain number of quantum qubits. Okay. Mathematically speaking, you can always describe a state of n qubits deformed by n qubits using a vector of 2 to the n components. And applying the quantum gates on this particular state means apply linear operator matrices on this vector in order to evolve it into the steps of your quantum algorithm. Okay. So if you implement this kind of calculation on a classical computer, we will obtain an emulator of a quantum computer. But with this technique, it is possible to emulate a perfect quantum computer. And this is a very good point that we will stress later. And for a perfect quantum computer, I mean something with an infinite current time, no possibility of error in application of quantum gates, and so on. Okay, so a very perfect quantum computer that we can use to emulate, to test, for example, our quantum calculus. So why using a quantum emulator right now? Because right now we know that we have actual quantum computers. So what is the need to use an emulator? The need for emulator is very important today, okay? Because the key point is that they are able to emulate a perfect quantum computer right now. And the quantum computers we have today, although they are sufficiently rich in terms of qubits, so we have broken the barrier of 100 qubit in a real device, but they are affected by multiple sources of error. Okay, so in order to test, for example, a quantum algorithm, if you're writing a quantum algorithm and you want to test it, it's not good to test it directly on a quantum computer, because if the algorithms fail, you don't know if the failure is due by an error on a quantum computer or an error on your algorithm. Okay, So the one good idea is to test it on an emulator. So if with emulator can be used to say that it can be a good algorithm, then you can test it on a real quantum computer, studying also the noise and the other things. Okay, and of course you can also implement noise models on emulators. So if you're interested to test some particular characteristic of a quantum computer, you can implement it on an emulator and use it within your calculation. And of course, for this reason, an emulator is also a great weapon to study all the new emerging technology of qubits, because we saw that there is not only one technology that we are using today. And okay, what is so the role of HPC in a quantum computer emulation? Why we need HPC to emulate quantum computers? An emulator is a software that requires very powerful hardware. Okay, the discriminant is the number of qubits that we want to emulate. If you want to emulate up to a few tens of qubits, it is possible to emulate a quantum computer using only a simple laptop, for example. But after a certain threshold, however, it quickly became necessary to use a large amount of RAM to be able to store the quantum state formed by the qubits and work on it. Okay, and to have an idea, to describe a qubit, in fact, it's necessary to and sufficient to allocate two complex numbers, and they are formed by four real numbers. So which they correspond to the coefficients for the states 0 and the state 1. Okay, and the number of coefficients needed to describe larger systems doubles for each added qubit. Assuming you're working in double precision, for example, 4 bytes for each real number, 1 qubit will require 16 bytes of RAM. 2 qubits will require 32 bytes of RAM. But if you increase this number, for example, 10 qubits will need 2 to 10 to the 10 power times 16 bytes, and this is 16 kilobytes, for example. 30 qubits will require more than 17 gigabytes, and 40 qubits will require more than 17 terabytes of RAM. This is a very large amount of RAM. Okay, and consider also that the application of quantum gates inside a quantum computer is a natural phenomenon in some way. Okay, it's not something that you are doing calculation. But this is not true, of course, in a quantum emulator, because in a classical computer, you have to apply the linear operator to the qubit state. So you have to evolve the state applying large matrices. And when the number of qubits is very large, those matrices becomes very, very large. They are connected to the number of qubits with the power law 2 to the n. The matrices as a row and columns length equal to 2 to the n, where n is the number of qubits that you are considering in this emulation. Okay, so you also need GPU accelerator, for example, or another HPC accelerator in order to make this calculation in a time quickly enough to see the result at the end of your circuit. Okay, so right now is very important to realize emulators that are able to support the realization of quantum algorithms for the society, for the scientific community. Of course, what I described here is not the only kind of quantum emulator that we can create. This is only the simplest one, in order to give you an idea of what we are doing. We are also developing other kind of emulators that use approximation in order to emulate the largest number of qubits, because for the state vector emulator, if I'm not wrong, the maximum number of qubits emulated is something about 46, because it's very, very expensive. But it's also possible to emulate biggest quantum states using approximation and other techniques. Okay, and next slide, please, Valeria. Okay, thank you. And yes, I hope that this was sufficient to answer your question about the emulators and HPC. And so what we learned today in this webinar is the fact that right now, in this particular moment of in this particular period in our scientific life, quantum computing is an accelerator. It can be seen as an accelerator, as a GPU, as a multi-core programming, is an accelerator for accelerate some part of the calculation. Okay, and it's certain that there are future advantages in some application areas. Is proved, mathematically proved, such as quantum chemistry, optimization, quantum machine learning. We will have this quantum methods. And but we don't know right now what will be the final quantum computer that we will use in the future. Right now we have a lot of the different technologies. We have to monitor all of them, of course, but we have not to settle too early on one technology, and because we don't know what will be the winner technology that we will use in the future. And we have to build an ecosystem with the most promising technologies in mind. And don't forget that the hybrid algorithms are very important, because they will be the first algorithm that will exploit the HPC part of the accelerator role of the quantum computers. Okay, so combining HPC and the quantum computer will lead us to a new advantage, computational advantage in this field. And okay, and for the advent of the large-scale quantum system, we will be ready. We will need to create an efficient and comprehensive quantum software stack, and we will also evolve the development of new emulators. And yes, this is what we said in this webinar. I hope that it was fine for everybody. And I think that this is all for my side. Thank you for your attention.
So yes, now thank you for the presentation. And now this is time for the questions. We have received 2, if I have seen it well. And you can send us more in the control panel in the question pane. And my colleague Pascal will share it in the chat so it can be visible for everyone.
So I guess it's my turn to read them and to get us going with the answers. So the first question is coming from Matteo Mascagni, and he's asking, are there technology standards in order to implement the HPC quantum computers confluence, please? In other words, how can we integrate HPC and quantum computers together? Not sure who is, maybe, well, Danielle said yes, Chima and Valeria. Who goes first?
I can start, since I was presenting the quantum HPC integration part. So today, there are no standards. We're still exploring what is the most efficient way to integrate quantum within HPC. As I presented quickly, we see different modes, these co-located standalone models for integration, and then the tight integration. And for the loose integration mode, we need to figure out which is the best way to communicate between the HPC and the quantum device. So this is still under development. There are several projects on it going on currently. So hopefully it will be figured out in the short term.
Okay.
Thank you.
Yeah, it has been something that has been neglected for a while. people haven't thought about it, and it has been a real showstopper also for the algorithm people. So some algorithms really have problems because they are iterative and they need these fast times between the quantum computer and the classical systems. Plus, they also need to be considered, you know, that for example, the queuing system could already be a problem when you have an iterative algorithm, and these things have been neglected for a while, to be honest. I mean, this is a fast-moving field, and there are so many things to do at the same time that there wasn't such an emphasis put on it, but people are picking up on it, and first implementations which are simply for this and which help really a lot of applications to run are now coming up, and this is helpful for us.
Mm-hmm. Okay.
Yes. Short answer can be we are working on it.
Yeah. All right. Good. Next question in the same context. Question from Mike Gio, one of our colleagues. For the open standards, do you think this will emerge naturally, or is there a role to play for neutral academic players?
Good question.
This is a very nice question. Yes,
yes,
it's almost philosophical. and
the answer is what?
Yeah, it's possibly possibly you can answer it in hindsight. So what can be seen is that some of the global players are coming together in order to talk about some of the necessary tools. For example, when compiling the quantum computing circuits, and they want to develop standards. But the point here is probably that you have to take into account that also the European technologies need to take part here, and this is also important. They might have different requirements, and so it is very, very difficult to say it at the moment whether you need a neutral player, but I think a neutral player would help actually at the current point.
Mm-hmm. Okay.
Yes,
so the next question is coming. I hope I pronounced the name quite okay. Maybe Pascal can help me. Mark Durkin. Durkin. Sorry for this.
No problem.
Can we have an estimated timeline for quantum computing developments? Even if it's a pure estimation, it could be useful for hardware and software.
So
it's a million-dollar question.
Very a lot of good questions right now, and I don't know. I can try to answer that. I can say that we have not, of course, a timeline for quantum computer development right now, and we can say that from here to, I don't know, 4 years, 5 years, we are confident to develop some very nice integrated HPC/QC systems. So we will see the first accelerator, quantum computers accelerators operating within classical computers and HPC good classical computers. But when we will see universal quantum computer, we don't know. We don't even know if we will see, but we hope we will see it in the future. But it's a very nice question that maybe, I don't know, maybe Pascal can say something more about that, because they're actually building quantum computers, and so they are more informed on it. But yes, what I can say with a sort of reality right now is that we are working on the integration of HPC and quantum computers, and we will see it in a few years.
Yeah, maybe I can comment. Exactly. So what I can say is that the technology is really developing super fast. that what we were expecting to last 3-4 years now is coming in 1-2 years. So it's going faster than what we expect. We expect the first quantum advantage to arrive between 2023 and 2025, meaning that we are not in the fault-tolerant systems. The quantum machines will not be corrected in error, but we will be have large enough systems to demonstrate a quantum advantage on real-world applications, on some optimization problems, some quantum machine learning problem, etc. And the fault-tolerant systems, as Daniele was saying, it's more difficult to have this estimation, but from what we see today, we strongly believe that it will come in the 10 to 20 upcoming years, which reduce it from the 50-100 years that was expected before. But again, it's hard today to give this estimation on the fault-tolerant systems.
Okay, so there are so many questions coming. We need to make a decision very fast that if we cannot answer them all, we are going to collect them and provide them to the team here and basically give the answers back to the entire audience. So the next question is coming from Carsten Kutzer. And this goes like this. When using the QC, quantum computing, as an accelerator for HPC, what is the amount of data in order of magnitude that would be transferred between HPC and quantum, the accelerator? And how much impact does the network latency have between both parts? So the HPC part, classical part, and the accelerator based on quantum computing.
Okay. Shall I say something? Okay, good. So as usual, we seem to be the people who are saying it depends. So I will go with the it depends. So the point is that it depends on the number of iterations. I mean, like how much latency actually plays a role depends on the number of iterations that you actually need to take into account. And here you can use very different optimizers, and some of them don't need so many iterations, while others take a bit longer to get you to the best solution that they can find. And this is also still in the field of open research to look into this optimization, and this could be also very problem specific. That you would have something where you can use use some previous knowledge, for example, or you can predefine your problem that it is at a good starting point and stuff like this, and that's what people are doing. Concerning the data transfer between quantum computers and classical computers, actually you cannot you're not going to send a lot of data, so it's not limited by bandwidth. However, what the problem is in your quantum algorithm, that you need to encode and decode the data, and that's very often where you lose a quantum advantage. For example, you would have quantum Fourier transformations where you can prove it's going to have a speed up, but if you don't have it in an application where you just have like one readout and you have like a long thing running, then you are immediately losing this speed up again because of the encoding and decoding of data. But that's directly on your quantum device, so it doesn't have to do with the integration.
Okay, good. Thank you. All right. I think we can still take a few.
Yes.
All right. So a question from Guy Lonsdale. With the hybrid quantum computing, so HPC and quantum approach, won't we see something like Amdahl's law playing a role here, which means the maximum speed up is dominated by the part, quote unquote, left on the HPC system?
Okay. The Amdahl's law is something related, of course, to the maximum part of a code that you can parallelize. And I can say that in this case, it depends on, I don't know if there is an equivalent of the Amdahl's law in this context, because then, in theory, a quantum computer can solve, of course, problems that are suitable for its configuration. So if you have a problem that can fit on a quantum computer, you can solve it using a quantum computer. But of course, you cannot use only a quantum computer, even when we will have a universal quantum computer, because you always will have the need to translate the results using a classical computer as a server and for the input output, etc. So I don't know in what sense when we can see the Amdahl's law in this context, but yes, I think that there is no an equivalence of Amdahl's law. The constraints are due on other things, on the fact that on a single algorithm is not feasible that all the algorithm will be processed by a quantum computer, because the spirit to realize HPC and quantum computing algorithms, hybrid algorithms, is that we have to identify the parts that are good for a quantum computer and the parts that are good for an HPC computer. Okay, so I think that the constraint is this one, but I don't know if there is if we can say that there is an Amdahl's law also for this kind of algorithms.
Okay, thank you, Daniele. Next question come from Jesus Ramos Rivas. It has been said that quantum computing will bring forth the end of effective cryptography. What credibility do you give this statement? Is there any work being done towards reducing the risk?
Okay.
So you're all nodding. So who wants to speak?
I don't know. I can say words.
Shaima, you haven't spoken for a while. Go for this one.
Okay, go Shaima.
So, there are some works done on the post-quantum security and cryptography to protect the system and encryptions once we reach the universal or the fault-tolerant systems. But again, we talk about these algorithms, the Shor algorithm, etc., that can break down all the encryptions. Well, not all, some of the encryption, to be more precise, and this will not happen in the short term. And I personally don't think it's a risk on the short term. It will be rather in 10 or 20 years. But there are some companies, startups in particular, working on the post-quantum encryption.
Any other comments, Valeria or Daniele?
Yes, it's, what Shaima said is totally true. Of course, when we will use Shor algorithm, it will be a problem for our bank accounts. But since the realization of a universal quantum computer, we can be we can stay calm. It's not a risk that we are running right now. And when it will be a concrete menace, I'm sure that we will realize some other algorithms like the post-quantum cryptography algorithms or the quantum cryptography algorithms that are developing right now.
Okay, good. So the last questions. There is one more coming from Fabio Affinito. Are there planned projects on co-designing QPUs as accelerators? What about EU funding in this direction? Not sure whether you can answer this.
So maybe I can talk about a project HPC for HPCQS. It's a European project to have this pilot program installing 2 quantum machines in 2 European HPC centers in the TGCC in France, the machine acquired by the GENSI, and in Jülich Supercomputing Center in Germany. So this is a pilot project to start integrating quantum processor within HPC. Co-designing QPU, it's a topic that that is very important, and I think should be looking into it with much attention. And we talked in the white paper about public funding such projects, because as we said from the beginning, the technology is still emerging and the development cycle is very short. So there is some risk in developing or selling this technology to private actors. That's why it makes more sense that public entities invest on this technology to buy them and co-develop them, etc. And having European projects funding dedicated to this, it's very important for the development of quantum computing in Europe and for the sovereignty of Europe in general as well.
So since we're running over time, I would like to just bring forward the last question. And then all the other questions will be answered via mail. So the last question from Marta Ivanovas is, as workloads are moving into a quantum environment, do you see any of the use case optimization happening in the cloud?
As workers, do you use? Yeah, I mean, like the quantum systems. I mean, the major quantum systems are connected directly to the cloud. I mean, they can be accessed via the cloud. Clearly, I mean, yeah.
Yes.
It's a yes.
All right. Yeah, I think this question is more like, are they cloud-based offerings of quantum emulation approachable by anybody?
Yes. It's not only emulation, also quantum computer. Yes, using cloud, it can be possible to use also emulators and quantum computers right now.
Okay, good. So there are a few more questions, but I think we're running out of time, and for sure we'll get you the answers. I would like to give this back with a big thank you to the team, to my colleague Maria.
Yes, thank you really for all the presentations and also for answering the questions. All the remaining ones we will answer via email. And I just would like to ask you to please fill in the survey just to give us feedback on the webinar and help us improving the future sessions. And thank you all for being with us today. And I really would like to wish you actually a very happy holiday season too. Have a nice day. Bye-bye.
Thank you.
Bye.
Have a nice day.
Bye-bye.
Bye-bye.